notes.
Sure. Week 16, day 1. So your Quadtree assignment's going to be due next Tuesday. So you're going to
Can I get
have...
an extension on that?
What's up?
Can I get an extension on that?
You're not in the class. Okay. So we're gonna be practicing today with quad trees. We've talked about it a little bit before. Basically, they're a data structure that has 4 kids. It's a tree structure where you've got 4 kids at every node, and if you have a rule that you can have no more than 1 point within any one square, if you add another point, you click. Then you got to divide it into quarters and do that. So quad trees are a great way of doing collision detection and things like that, because areas that don't have any things in it, you can zip over them pretty quickly. Like if you shoot a line, the line comes in here, it's like, that box is empty, cool, I don't have to do anything. And then you just do the line equation to figure out where the exit point is, right? So like if you have mx plus b, here's x, 0, here's x5, you just compute the exit point. And then, that one's empty, you just hop across it. And so you can do ray tracing pretty quickly in a quad tree. Collision is pretty easy. If you're going to say, hey, I'm right here, do I collide with anything? You just have to check within the little box here and be like, all right, he's here, I'm over here. Nope, doesn't collide. And so you can find the square in order log in time, and you can then hunt within the square pretty quickly. If you allow 1 point per square, then you just check to see if you touch the 1 point. Sometimes, though, you allow multiple points in a square, and if you allow areas that are bigger than just a point, then you have to handle the boundary splitting them. So you have to. So this circle here would be both in this rectangle and this rectangle here. And so you'd have. So basically, each quad tree would have a list, and the list would be like indices that are the objects within it. So let's go ahead and do that. Let's start off by making a struct quad tree. And we could probably set some parameters in this, maybe using template parameters or something, like an int.
Do you need a node, like a left and right node, kind of similar to a binary tree, since you have like 4 nodes for each tree?
Yeah, except there's 4 instead of 2. It's a quad tree instead of binary tree.
Oh.
So we need to have maybe a limit of like how many objects we can have at most. Because when you start having like rectangles and stuff, it actually gets really hard to divide them and kind of like get down to just 1 per area. So you end up creating these
So how
really...
do you use a quad tree though?
Like this. Use them... no, that's shaders. So let's say you've got a surface like this, right?
Oh, okay, that makes sense.
And
so instead of like boxes for collision, we'll just do like a smooth. Looks like you're integrating it basically.
Well, so let's say your ball is here.
Yeah.
So the ball is to the top left of the center part of the tree, right?
Yeah.
And so you say, all right, I'm going to check the upper left kid. And the upper left kid has nothing in it. So does the ball hit anything? No. Done. Yeah. And so rather than having to check all the different objects in the world and checking all the different things that are all moving around and stuff like that, you're just like, nope, doesn't hit anything. Done. And you just call it a day. Now, if there is something like in that region, then you have to traverse down the tree. And so tree depth can become an issue. Like if you have like these super, super deep trees, then actually traversing the tree can actually be a problem. And so there's different heuristics and things we do to try to minimize the hunting time to find the right region. But yeah, basically they're really useful for like collision detection, if you're going to do ray tracing, if you're going to do a hit scan attack, if you want to find out who's near you, you can start at a point, and then if the radius search is smaller than the box, it's very easy.
So like for example, if we're colliding into a square surface, possibly.
Yeah, like with this one, it's a
so like that's how it would be used for. So for example, if we're trying to get to collision, so it could be a smooth collision instead of like a boxy collision. You would use that.
Well, it's still a boxy collision, but it's just a small. The details are small enough that you don't notice that they're boxy.
Yeah.
Yeah.
That's what I'm trying to say.
Yeah, and so
yeah, I've actually had this problem when I was developing my platformer in high school.
Mm-hmm.
I always had to make everything really blocky because I didn't want any like weird like collision errors.
Yep, and so when I made my engine, it was a hierarchical bounding volume using spheres, and yeah, if things weren't spherical in shape, then there would be noticeable errors. Right, like you'd shoot here.
I would imagine because it'd be rolling around even though it's not a sphere.
Oh no, I didn't have it rolling. It was just for collision. And so, like, if you shot a hit scan weapon here, it would say you hit the plane, you know. And so I kind of had to make sure my art and everything were roughly spherical in shape. All my robots, all my buildings were roughly spherical in shape, and so you just wouldn't notice the fact that my bounding volumes were spherical.
And that makes sense. That makes a lot of sense, actually.
And the reason why I did that is because sphere collision is super fast. It's super easy. So it was just a speed. It was a speed thing. This is back in the 486 days where we had 33 megahertz CPUs, and so doing everything I could to make every frame you have to do collision, right? And having a sphere is, you know, especially in a bounding volume, so you can just have a bounding volume that's a sphere, and if you're outside of that, you don't touch it. Done. You know, it's just one test. And these are progressively. I didn't use a Quadtree for that engine, but a Quadtree is. Let's see if I can find a shot of it.
Because I would imagine let's make that easier to collide with, so you won't notice the boxy collision.
Yeah. So see if they have one with boxes. Maybe that one. No. That one. No. These are all kind of like points. These are like point collision.
No, actually talking to you about it makes this a lot easier.
Yeah. Okay. Here's one. So yeah, so you have different boxes and whatever in the world, and then if you want to see if you collide with something, what you do is you have to check just the region that you're within, right? Oh. So like if you're completely enclosed within this region here, the only objects you need to see if you hit is this one and this one, right? And so you just go down the list, and then you can do a very accurate collision test if you want, with a convex hull, and you can do convex hull versus convex hull, which is fairly expensive as these things go. But because there's only two objects nearby, like, yeah, it's fine. You know? Or,
May I have your attention, please?
I'm sorry. It's just, yeah, I'm sorry. I'm at work right now, and our security system doesn't work because our building's basically new.
Mm-hmm.
So I'm sorry.
No worries.
Really quick,
yeah.
Could you change the region if need be to then check for another sort of collision?
Yeah. So once you kind of get down into the leaf node, then you can do an actual collision check, right? The whole point of a Quadtree is that you've got all these different points all bouncing around, and by default, like let's say that you're simulating like gas within a balloon, right? And all these helium and hydrogen and whatever atoms are all bouncing around, right? And you want them to collide with each other, right? Because that's how you simulate gases, right? Because the faster things are moving, that's the temperature, right? And so the faster they move, and then when they hit the edge, that's pressure, right? The pressure you feel on a balloon is the net impact of the gas hitting the wall and then reflecting back off, and so that's what pushes the balloon outwards. And the hotter the gases, the faster they're moving, the more they push on the elastic, boundary, and the balloon gets bigger. And so you want all these things to be bouncing with each other. And by default, that's a painful thing, right? Because like you got, yeah, it's very costly. You got like I don't know, 10,000 gas atoms or whatever. And so by default, you would have to say for every gas atom, see if every other gas atom is touching me. And
this is like an O of it's like really high n value.
It's an n squared algorithm, right?
Yeah, n squared.
Yeah, and so if you have just 10,000, which isn't even that many, you'd have 10,000 times 10,000, which is like what, 100 million or something.
100 million calculation, probably.
100 million calculate, yeah. And instead, you could do it in log n with a Quadtree. And so with a Quadtree done right, you can it'll subdivide the world like this, and then you can traverse down it. You'd say, hey, tell me everybody near me or everybody within my box, because those are the only people I could be hitting, you know. And there's an issue if you're on a boundary like this, right? Because then you have to search in this box and this box. And if you're across 3 of them, you have to search in that box and that box and that box. And so there is a problem to having the Quadtree get too small, because you end up having to check every box anyway, you know. And if you have a circle that encompasses the entire area, you end up having to search the entire thing anyway. And so there's certain trade-offs and heuristics and things like that that kind of make it fast. But the ultimate goal is that if you have 10,000 gas particles, you should be able to do your collision in roughly 10,000 times the log base 2 of 10,000, which is not a large number. What was that like? Log base 2 of 10,000. Log base 2. 13. So 130,000 instead of 100 million. So 1,000 times faster.
So that's really good efficiency wise.
Yeah, it's not bad. And when I did my collision detection engine, I actually just used something like this. Like, it wasn't a Quadtree, it was just a regular grid. And then when things would move, they would pull themselves out of the grid they left and put themselves into the grid that they entered. And then when they did collision detection, they would just check within the grid they're in. And there was a...
Yeah, that makes sense for like really low resolution screens, though.
Mm-hmm. Yeah, and it was tricky to implement because they weren't points; they were spheres, right? And so if you intersected multiple spheres, then you had to put yourself in this one, this one, this one, and this one. When you left, you had to remember to delete yourselves from the 2 that you're leaving. And it was kind of you know. And if you got a rounding error or something, you might leave yourself in the point you actually left, and that's a pain. And so there was these like fiddly little like implementation details that made it a lot harder to write than it really should have been. Like, it actually shouldn't have been that bad, but because you add yourself to a point, and then when you move, the rounding error goes the other way, and it says, oh no, you weren't in that point, and it leaves you behind. And then when you get destroyed, let's say, you pull yourself out of the collision table, there's still a pointer in there to you that is now pointing at a deleted object, and the thing segfaults and crashes. That
can lead to a memory issue, isn't it?
Yeah, segfault. It was crashing. It was crashing due to rounding errors.
That makes sense, because when you're pointing to something that doesn't exist, you're basically just exerting your memory for something that doesn't exist. So it's going to probably lead to an issue where you have memory.
Yeah, it was a massive pain to actually, like, getting it to work was easy. Getting it to work and that's the thing you'll encounter a lot when you're doing numerical stuff, is that just dealing with
usually if that ever happens
errors.
to me, I just cut the feature entirely.
Yeah.
But you didn't have a solution though.
Yeah, it's like, all right, you know, what are you gonna do? Like, you know, you gotta have something, because otherwise it runs too slow. And so, you know, maybe when you die, you just go through every bucket and and just check every bucket to make sure you're gone, you know, because you don't die that often, you know, like, you know.
That makes sense.
So, you know, you can maybe pay a little bit of a cost on death, you know.
Let me get my IDE open.
So, all right. So let's just do this. So we're going to make a Quadtree struct. And so the primary feature of a Quadtree... Why is my frame rate so low? Do I still have Shader Toy open or something? I think it was exercising the hard drive. What do we got here? Network. NordVPN, a little bit. Streaming. Still uploading.
You have the NordVPN going on in the background.
I do, yeah. Yeah. There we go. All right, we're back. So every Quadtree, the primary feature of a Quadtree is that it's got 4 kids, right? So it's got the upper left, and we'll just do this. The upper left, the lower left, sometimes I call it down left because L looks like a 1, you know. If I could spell Quadtree. How about that, huh? All right. Quadtree, YY3T. Maybe we'll call it down left. Keep it on the DL. Upper left, upper right, and down right. Okay. And so by default, they're all null. And we could, say bool leaf equals true. And so we can just keep track if we're a leaf node. All children will either all be null or all will be set. Okay. So if we have to divide ourselves up, we set all of them. Okay. And then the other thing we need to do is know what region of space we cover. So int min row max row min column max column. And sometimes people will do this with not max but with size, so you know how big you are instead of the min and the max. I kind of go back and forth on it. It kind of depends on my mood. We'll just initialize all these to 0, I guess. All right. If min row equals 5, max row equals 10, then we have a height of 6, right? Okay. 5, 6, 7, 8, 9, 10. Okay. So it's inclusive. And I always like to put these things down just because sometimes it means not including the max or something like that. So, but I think it makes sense. If your min is 1 and your max is 1, you're at 1. So kind of makes sense to me though. All right. So we got all this, and then we need probably an insert function, right? We need an insert function to add a point into the quad tree, and
Would we use a class for this?
This is a class, yeah.
Yeah, but that again, that makes sense. Yeah, you're right. You're right.
Yeah, sure. Yeah. Okay, and then we need to have an insert function. We need to have a search function, and we need to keep track of if there's a point within us. So let's make a point. Struct point, and it's just going to have a row and a column. Okay. And so bool empty equals true, and if it's not empty, then point point. So we need to have insert, we need to have search, probably render maybe as well, so we can draw it to the screen. We use the colors library for rendering. So right now we can either hold a point or not. So leaves hold a maximum of 1 point. Okay. If you're not a leaf, oh, hold and anchor. Okay. So let's do this. Friend iStream. So we'll write a function to read from the standard input into a point. And so we'll just cn into row and column.
Okay, now you're operating overloading.
What's that?
Okay, so you're operating overloading now?
Yeah, I'm just going to make it easy for us to read p.row, sorry. It's a friend function. There we go. Column, there we go. So we're going to read from the standard input into a row and a column to make it easy to just read a point in. And then I don't even know if I need a double left arrow operator. I'll write it if I need it. Let me see how
I'm putting input operator. So basically, yeah, that would work. That would work. And then easier to do one scan statement.
Okay, while true. While true, point temp equals read. Please enter a row and column for a new point to add a Quadtree. And then we will make a Quadtree, of course. Quadtree QD, why not? Okay, and then oh yeah, we need a break, of course. 0, 10. Actually, negative number. Any negative number will end. So if temp.row is less than 0 or temp.column is less than 0, break. Okay, so then we will say qt.insert temp. There we go. So there's our user input. We just need to write the insert function, of course. That's what's mad at us. But what this will do is it'll prompt the user over and over again for a row and a column, and it'll just add them to the Quadtree. And then the Quadtree algorithm itself is pretty straightforward. Oh, the Quadtree needs to be initialized, though. Yeah. Okay. All right, we'll come back to you in a second. Let's see here. Auto get we call it grid screen. Get terminal size.
Really quick, that one of the first row that you highlighted where it has auto, what does that exactly do again?
Yeah, auto just changes its type to match it. I think. I'm pretty sure.
Yeah. So what this is called structured binding. So get terminal size actually returns two values. It returns how many rows you have and how many columns you have. And so this is going to.
Program in the class because I'm running Visual Studio Code for this.
So this is going to set rows equal to the number of rows on the screen. This is going to set columns equal to the number of columns on the screen. I'm going to subtract one off the number of rows. So we don't scroll the screen. In PuTTY, if you print to the last line of the screen, it scrolls up, you know? So I'm actually going to make the screen a little bit smaller in the vertical direction so it doesn't scroll when you do stuff. Okay, so we're going to make the Quadtree and that, and then I'll just do it this way. Min row equals 0, max row equals qd.max row equals rows, max call plus columns. So we're basically making the Quadtree encompass the entire world, right? And the minimum and maximum is the top left corner, 0, 0, bottom right corner, and is it empty? Yes. Is it a leaf? Yes. Its kids are all null. Okay, everything else is fine. So that is all we need to do to set the Quadtree. That's all fine too. We should probably also bounce check it. So if temp.row is greater than or equal to rows, or temp.column is greater than or equal to columns, then just continue. So if they type in 500, 500, it'll just ignore it and throw it away. So we'll only put points that are on the screen.
Yeah, we should do the same if it's less than 0.
Yeah.
For example, I accidentally
right
type
here.
in -1, it would just break it, right?
Right here.
So,
So
but as soon as you break it, the program ends.
it breaks out of the loop. Yeah, and then the program ends.
Oh.
Yeah. So I'm covering the negative. Negative ends the loop. If they type in something too big, I just ignore it and then reprompt again.
Okay.
Because I say just type in a negative number to end the input phase.
That is actually a really smart way of doing that.
Cool. Thank you. All right, so I think we're all set up here. We just need to do insert now. So here we go. So Quadtree insert, and this will take in a point, const point by reference p. Okay, so the point's going to run a column. We got to run a column. We need to figure out, I guess, what our midpoint is. So maybe we should hold a midpoint and a size. No, because it could have an off by 1 error if it's not a power 2. Okay, so we're going to be inserting into this, and we need to find out, is the point above, which of the 4 quadrants is the point in, right? Does that make sense?
Makes sense.
Okay, so if we are a leaf node and we're empty, then we just add it to us, right? Because a leaf can hold at max 1 point. So if we are a leaf and we are empty, then point is equal to p, and we return. Just copy that. Okay. So when we start off with a blank Quadtree, covers the entire world, we add 1 point. We're like, cool, that's our point. You know, easy.
Okay.
And we can even do search, you know, and just say if the points match, then return true. You know, if not, false. Pretty easy when you've got 1 point in the entire tree. So if we're a leaf node and it's empty, okay. If we're a leaf node and we're not empty, then that means we're gonna have to split. Like if we're the entire Quadtree and we already have a point in it and we're adding another point, now we need to divvy it up. Okay. So if we are, before we check that, let's say we're not a leaf. So if we're not a leaf, we're gonna just pass. We're gonna pass the point to whichever child we have, right? So if it's in the top left, we're just gonna say, all right, you handle it, pass it off to them. So if we're not a leaf, we need to figure out which quadrant this thing is in.
We could just do a bounds check and just check each one if it's filled, right?
What's that?
We could just check if those whatchamacallit, right, left pointers are actually pointing to something. That could be a way of solving that.
Mm-hmm. But we need to know which of the 4 kids to insert into, right?
Okay, yeah.
So we're gonna have to get our midpoint, and so midpoint row is equal to min row plus max row divided by 2. And could this cause a problem? Maybe. If we ever get down to size, if we ever try inserting, we should probably, if we ever have a duplicate insert, this is going to go into an infinite loop, I think. Because it'll try inserting into a size 1, it'll split, and it'll still be size 1, and it'll split, and, you know, so.
Probably even worse if it's 0.
Search for duplicate and discard. Yeah, so if the size is 0, if min is bigger than the max, there's a lot of...
Yeah,
there's
0 to 0, and dividing 0, it's
still gonna be 0 in that case, but like if it's 10 and 10, you get 10. If it's 9 and 9, you get 9. That's not really a problem. The problem is that when you try to divide a Quadtree of size 1, you can't divide any further, you know, and it'll probably explode. So that can only happen though if you are inserting a duplicate. So if you've already got a quadtree of size 1 and you insert it into that spot again, then it'll try splitting, and so you just have to check for duplicate first. That's all I'm saying. Okay, so okay, maybe we can actually do that right now. It's not how, because 0, 0 is a valid point. So if we'll just set it something invalid just to be safe. So if p is equal to point, then return. So if, do we need a double equals operator? Oh, const pointed point.
Yeah, because you're doing a comparison, so you're getting a double. Okay.
No, it's just point and point. Okay, it doesn't do double equals operator for us anymore. It's fine. All right, so bool operator double equals point reference const point reference other. So return my row equals others row, and my column equals the others column. So if they both match, it's true. Otherwise, it's false. And then are you still mad at me? Still mad at me? Don't like that? To be ambiguous.
How do you get errors to show up on Vim?
Secret. Okay.
No.
All right. So if there's a duplicate, it's fine. So if we're leave it empty. Okay. All right. Yeah, but we should only do that if we are not empty. Okay. If we're not empty and the points match, it's a duplicate. Throw it away. Okay. So midpoint row is that. So that'll handle the degenerate case here. Midpoint column is equal to the average column. And then we just need to determine if it's up left, up right, bottom left, bottom right. And so we're going to do some if statements, I guess. So if the points row is less than or equal to midpoint row, bool above, let's do it this way, bool left. Okay, so we have a Boolean true or false. Is it above us or on the midline? Is it to the left of us or on the midline? Good to go. All right, so okay, so where are we? We now can tell which quadrant it's in. We're handling, if we're empty, we now have a point. Oh, and we're not empty anymore. Yeah, empty equals false. Definitely need that one. So we're not false anymore. Okay. Okay. So we can be a leaf and empty. We can be a leaf, not empty, or you can not be a leaf. Those are the three possibilities. So these are the three possibilities, right? You can either have nothing in it, in which case you just do this one.
Yeah, because you basically have all the cases set up. Because you're just trying to see if there's a leaf and it's not empty, and you just split it, right?
Mm-hmm. Okay. So if we're a leaf and not empty, if we're not a leaf, actually that's probably even easier to handle. All right. Do that one first. So if we're not a leaf, then
still trying to keep up here.
Okay, so if we're not a leaf, then what we're going to do is we're going to recursively insert. So we are going to insert into our child. So if above and left, we're going to call our up left child, insert, passing the point, call it a day. So if it's above us and to the right, we call the upper right insert. If it's below us and to the left, we call the down left. And if it's below us and right, okay. So if we're not a leaf, then we just pass off the insert to our kid. I'll let them handle it. Perfect. And then the split. Let's handle the splitting. Okay. So if we're not a leaf, we just pass it off. And then if we're going to split, then we need to set leaf equal to false. Okay. So if we're going to split, we're not going to be a leaf anymore. We're going to create 4 kids. So we're going to say upper left is equal to new Quadtree. We're going to need to pass in min row and max row, I guess.
My God. So you're just gonna keep doing that? Basically, if it's full, you just basically. I'm trying to figure out how to do this. Say, leaf is not empty. It's a leaf. It's not empty.
Yeah. So if we already have 1 in it, then we have to split into 4, and we're going to pass off. We're going to pass off our current point.
So if you get 1 left, you just pass off the next one.
Yeah. If we already have 1 in here and we're inserting a second one, then we need to split. And and then we're going to call the. We're going to do this on both of the points, both the current one and on the new one. I might need to move that code down because it's going to be duplicated. So the key thing here is figuring out what quadrants these guys are on. Okay.
Yeah, if you do the midpoint to find the quadrants.
Yeah, and that's why we did the midpoint exactly. And so the order of this thing, I'm just going to copy and paste so I can keep an eye on it. This is the order I did it, so that's the order I will.
Yeah, I kind of gave up on following you because I was like putting along and I'm like, wow, you're already there.
Oh, class ends at 4. So. Okay, so the minimum row is our minimum row. The maximum, this is the upper left, right? So the minimum row is our minimum row. The maximum row is going to be the midpoint. And then the minimum column is the upper left. So it's going to be our minimum column. And the maximum column is going to be the midpoint. Then let's do this. So for the upper right quadrant, the rows are going to be the same because it's the upper part, but the starting column is going to be midpoint column plus 1. So it starts off to the right, and hopefully this doesn't go out of bounds. And then it's going to go to our maximum column. And there's quite possibly going to be a problem with that because we have to bounce check.
Yeah, if you're running 1 over, so if you put like 50 nodes in there, it's going to eventually go out.
Every time you split it, it's splitting along the midline, and then it's going 1 to the right of the midline. So I think as long as if we split right on the edge, then it would go off the edge.
Or you can do some bounce checking too if you want to do that. But the problem is, as soon as you bounce check, you won't get all the quad trees you need.
We'll come back to this later. I think it should be fine because we're not allowing us to split a size 1 quadtree anymore, which would cause that problem. So I think we're fine. Okay, so down left. The columns are going to be the same as before, but the min row is going to be the midpoint row plus 1, and then it's going to go to max row. So it's going to be midpoint down, and then left to the midpoint. And then for you, it's going to be you. Okay, so these are the 4 quadrants. That's the hard part on a quadtree. It's like you got this big rectangle. You have to split it into quarters and say you're this region, you're this region, you're this region, you're this region. And then, basically out of time, so I think for
So the assignment is that we're going to port it over from Python to C++?
Yeah, or you can start with my code here. The YouTube video I gave you runs through the whole thing. I'm showing you a C++ way of doing it, and so this will be probably a good start for you. I got to go pick up my kid.
Okay. One question before we leave. Did you check my final project yet? I sent it to you on Discord.
Which one?
It's a Tetris clone I made in JavaScript.
I haven't looked at it, but you want that to be your project?
Yeah, I've been working on it for a while.
Yeah, sure. Yeah,
let's try it out. Just see if it's good enough. If it's not good enough, I'll work on something else.
Yeah, no, I'm sure it's fine. I think it did look at. I think it did look at it.
Last semester, I just decided to do a Tetris clone. So I actually like Tetris.
Gotcha.
It was frankly very popular. It was
Nice.
one of my more popular JavaScript projects.
Okay. And so, so when we split, we don't just have to pass the point that we're inserting down, but we also have to pass our current point down as well. So 2 of them are going to get passed down. So, so our current point yoink. I guess technically you could probably hang on to it at the current level, but I only want the leaves to hold points. So pass the point down to a new kid, and then this could possibly cause another split, right? Because they could go to the same quadrant, then it'll split again, and that might be the same quadrant. It'll split again. It'll split again. So. And then we need to do this first, just to stop splitting if you have the same exact point, because that'll infinitely recurse. All right, so I think that's it. I think it's the code, and I haven't run it yet, but I'm confident it will work properly the first time. And
No compiler errors. Hopefully. It's so tough with using Vim because I don't know what I'm doing wrong until I compile it.
Missing initializer for Quadtree point. Yeah, I don't care. No errors. There we go. Just warnings. Clear screen. No warnings now. Okay, so I'll throw up main.cc into public quadtree.cc, and I'm sure that is, you can grab that out of there. I'm sure it is a fully functional and absolutely bug-free implementation that I made for you. So you're welcome. You can start with that, or you can just run through the tutorial I posted where the guy does it in Python, and then you can port from Python into C++, which is also a good exercise for you. So either way you want to do it. The basic
I
will...
feel like I can do Python port because I actually use Python on a daily basis.
Okay, it doesn't crash on a duplicate. That's good. No seg faults. Yay, I call that a win. Okay, we don't have a search done, and we don't have.
What's the visualization look like?
The visualization, the most basic one is you just draw the point if you have a point, and so you use the move cursor to move to the row in the column and draw a white box there. But what I was actually thinking about doing myself was actually having the Quadtree draw the grid. So for the midpoint in the column, mid row and mid column, actually draw a line across and down from mid row to max row. You know.
Okay.
And then you can actually see the Quadtree as it subdivides and things like that. So we're out of time for today, but I think that's probably enough anyway. I don't want to do all of it for you, but that's kind of the idea.
Do we have a extra credit thing during Thanksgiving?
It's not extra credit. We're just going to be playing games on Black Friday, 12 to 4.
Okay.
If you need extra credit to play games, I don't know.
I'm joking. Okay.
Yeah. It's just fun.
26 is hurting me, man. It's hurting my confidence. Like, I showed one of the Readly tutors are 26, and it's like all they do is Zy books over here. Like literally, someone came in just for Zy books. Sounds like Fresno State.
Yeah. Anyway, I have to get my kid in 3 minutes. So
yeah, you know what? I
got
you.
you.
I'm gonna go to 7-Eleven real quickly before I start my next shift.
See you, Duncan. Thanks for coming out, you guys. See you.
See you later.
Bye.